Okay, let's start. Good afternoon, everyone, and welcome to this URASIP webinar. My name is Ignacio Santamaria, and I'm going to be chairing this session. First of all, some announcement. Just for you to know that the session is going to be recorded, except for the Q&A part. So let's start. It's my pleasure to introduce our speaker today, Professor Bruno Clerckx. Who is full professor at Imperial College, where he leads the signal processing group. And I think that before that, he spent some years in industry as well as in Austria and also later in Samsung Electronics. Well, he has a very long career, very successful career with many significant contributions in a wide range of wireless communication problems and standards. But probably his recent contributions to non-orthogonal multiple access techniques like rate splitting are very well known and relevant, and also his recent work on reconfigurable intelligent surfaces, and specifically probably the beyond diagonal architecture, which I think is going to be part of his talk today. So, well, he has published extensively in all these fields with a huge number of journal papers and what is also very remarkable, many contributions to standards and well, he's the inventor or co-inventor of nearly 80 patents, which is truly impressive. So on top of that, he has received many prestigious awards like the Blonde Medal from France and the George van der Linde Prize in Electromagnetism and Telecommunications from Belgium, Royal Academy of Belgium, and of course, multiple best paper awards in journals and conferences. So without further ado, I just want to thank Bruno for taking the time to give us this webinar. And please, Bruno, you are sharing your screen, so the floor or the screen is yours. Thank you.
Thank you very much, Ignacio, for the kind introductions and also for inviting me. Thank you also to URASIP for organizing those webinars. So as Ignacio mentioned, I will be talking about reconfigurable intelligent surfaces, in particular new advances in intelligent surfaces that are called those beyond diagonal intelligent surface, or beyond diagonal RIS, or BD-RIS for short. And then the step beyond that, how we can use some of the ideas of this BD-RIS to enable computation directly in the analog domains. So for those who are actually not familiar with Imperial College, we're located in the heart of London. We are actually in South Kensington. This is Imperial here. It's an old picture, but my building is right behind this logo here. So it's between the Albert Hall, which is a very famous concert hall, and those Science and Natural History Museum, and right next to Hyde Park. So if you happen to come to London, come and visit us. So our group of communications and processing has 12 academics, and we have about 90 PhD students and researchers. Active in communication and signal processing. So essentially signal processing for communications, for speech, for images, for some aspect of AI, some aspect of optimization. So yeah, feel free to come and visit us if you happen to pass by London. Right, so today I want to talk about how we can get towards doing computation more efficiently. We've been using digital computations or digital computing now, digital signal processing for maybe 50 years in all modern systems that we're using on a daily basis actually relies on digital computing and digital signal processing. And this is for very good reasons, that actually digital is very robust against noise. You can store, it's secure. So it's lots of advantages. There are also some limitations in terms of clock speeds, in terms of computational complexity when the problem size grow. And maybe more importantly, that actually our world is inherently analog. And so when we perform computation digital, we have to actually digitize our inputs via analog to digital converters, and therefore also digital to analog converter when we want to actually interface between the digital world and the analog world. And we know that those ADCs and DAC can be actually quite power hungry. Analog computing has a much older, a much longer history than digital computing. But in the past decade or so, analog computing has attracted a renewed interest because computation can be made very, very fast, almost at the speed of light. You can benefit from highly parallelized computations offered by analog computing and potentially make analog computing much more energy efficient than actually digital. And so I give you here 3 different fields where actually analog computing has seen a renewed interest in metamaterials. So how can you engineer materials to actually do computations directly? So the waves, for instance, light is impinging on the left side of these materials, and the material is actually is configured so that actually you can measure the output of these materials. You can measure some functions or some solution to some functions. Resistive memories arrays is a different type of analog computing. It's also called in-memory computing. So where you try to do computation directly inside the memories instead of doing this in the CPU, for instance. And so that resolved the problem of having to always transfer a lot of data between the memory and the CPU. Instead, you actually start doing computation directly in the memory. And also at optical frequencies or actually optical systems, so optical computing, photonics computing is something that is heavily researched in actually more in areas of physics. And this can be very relevant. Doing computation could be potentially very relevant in future communication systems that actually really live at this interface between digital and analog. So here I take a textbook diagram of a communication chains where you have multiple blocks here at the transmitter, the wireless channels, and multiple blocks at the receivers, and they actually conventionally implemented into in the digital domains or the analog domains. And the features of those blocks have improved over the past decades to improve to actually boost data rate, to boost sensing capabilities, to boost via an increasing number of antennas, larger bandwidth, and so on. And so if you take a 4G systems, for instance, where you use multiple inputs, multiple outputs, so multi-antenna signal processing, everything is done primarily in digital.
So let me take back a little bit. So I was talking about digital computing and analog computing and the re-emergence of analog computing in various fields, especially in physics, to do computation faster and hopefully more energy efficient. Right. So future communications or communication systems also rely on those 2 domains of digital and analog. So on the left side, you have here a communication chain with a transmitter, receiver, and the wireless channels. And as you have this sequence of blocks implemented in digital or analog domain. And the features, the properties have improved over the years to enable higher throughput and higher sensing capabilities. And on the right, you have essentially this evolution from 4G to now future systems, where in 4G, everything, for instance, the MIMO processing was done in digital. In 5G, you started seeing at higher frequency bands some form of analog beamforming coming up. And the objective was there to try to reduce the costs of digital, because digital requires 1 RF change per antenna. So it can be quite costly as you increase the number of antennas. And the question is, given this re-emergence of analog computing, what would happen maybe in future systems where now you have thousands of antennas and you may have to actually sense hundreds of data streams? So what I want to do today is how we can get there potentially by looking at 2 different fields. The first field is how we can take microwaves that are actually essential for all those communication systems or sensing systems, and how can we shape this? So being able to shape microwave is very important in order to actually do some form of analog processing or computing. And this is understanding what actually the optimal architecture we could come up with that gives us the maximum flexibility to shape microwave. And this is this area of beyond diagonal width. And then building upon that, I will look at how we can actually then compute with microwaves. And there it's this area, this emerging area with very few papers yet, of microwave linear analog computers, where we can do some computation directly with microwaves. Let's start with the first topics, and starting with reconfigurable intelligent surfaces. That is a topic that has been quite popular in the past several years. You have a transmitter, you have a receiver, and embedded within the electromagnetic environment, you have this intelligent surface, which is actually made of a lot of elements, ideally passive element, but they could be active as well, that actually are tunable. So the tunability or reconfigurability of those elements is very important. And you tune those elements in order to engineer the wireless channels and therefore engineer the propagations of those microwaves between the transmitter and the receiver. And conventional architectures that have been heavily studied for those risks are actually abstracted here with this figure on the left that I will call conventional risks or diagonal risks, and you will see in a minute why we call this diagonal risk. So physically what's happening is that you have those elements that actually connected to some form of tunable load, and by tuning that load, actually the wave impinging on a certain element or a certain port will actually be reflected with some phase shift, for instance, right? But importantly, you see that actually all those elements are disconnected with each other. So when the wave is impinging on element 1 or port 1, it will be reflected by port 1, right? Mathematically, what that means, how we can actually characterize this interaction between wave and the surface is via what is called a scattering matrix, theta, that is also called phase shift matrix in some of the communication literature. But essentially, this matrix is a diagonal matrix. It's a diagonal matrix that gives you the relationship between the impinging wave and the reflected waves. And so, for instance, here, this matrix is diagonal because the wave impinging on port 1 will be reflected by port 1 after subject to actually a phase change. And so this phase change is actually what you have here in the diagonal entries of the scattering matrix theta. But now if you have many elements in this surface, well, you see that actually you have lots of zeros in this diagonal matrix. And those zeros, you don't really make use of them to actually engineer waves or actually engineer your propagations. So what we would like to do is, how can we potentially make use of all those possible entries of the scattering matrix to give us the maximum flexibility to manipulate microwaves? And so the reason why it's called diagonal risk here is simply because this scattering matrix is always diagonal, right? So the field of beyond diagonal risk is how can we actually expand or generalize this concept of risk, where we don't restrict ourselves anymore to actually operate with diagonal scattering matrices. So potentially all the entries of the scattering matrix could be actually used. And what that means physically is that if you you can control diagonal and off-diagonal element of the scattering matrix, it means actually you interconnect element with each other within the surface. That means actually a wave exiting one point in space of the surface, actually a wave that has been impinging on different part of the surface have flown through the surface or crossed the whole surface before exiting the surface, right? And the question is, how would you do that? Why would you do that? When would it make sense to actually have those more advanced risk topologies for maximum wave manipulation flexibility? One thing that is important to note is actually how we model this, and I will come back to this in a minute, is the scattering matrix. If you have a completely lossless race and passive, the scattering matrix is not a unitary matrix, so theta is unitary matrix in the same way as what we had here. The theta on the left side was actually also unitary, but we are not constraining ourselves to actually have a diagonal matrix. And then this theta could be actually symmetric or asymmetric, leading to two different types of surface, either reciprocal surface or non-reciprocal. And this is something that is quite interesting. The non-reciprocity here is only enabled if you can actually operate those beyond diagonal risks. You cannot have non-reciprocal surface with a conventional risk because this theta matrix on the left side is always symmetric, right? So let's see why would we do that? Why would we create those BD risks? So the first thing we can think of is to have flexible arrangement and deployment. So you can use those BD risks in different setups. You can have in reflective mode, so the wave impinging on the surface will be reflected by the surface, but the wave will flow through the surface because elements of the surface could be potentially interconnected with each other, right? Then you could have surfaces, you can actually have two surfaces connected to each other. In this case here, one surface actually more illuminating the left side, one surface more illuminating the right side. You can have one element of the left side connected to one element on the right side, or you can have multiple elements on the left side connected together and connected with element on the right side. So that would enable you to have simultaneous transmissions and reflections, but in a very general case where you actually try to have maximum wave manipulation flexibility via those interconnections that you have among elements. Then you can have more fancy structures like in a multi-sector, for instance, where you can have multiple sectors that are actually interconnected with each other. And so wave could be impinging on sector one, for instance, would be reflected by that sector one, but wave could also flow across those different sectors because elements across the sectors are interconnected with each other. And that could enable you to have 360 degrees coverage, but also highly directional transmission in each of those sectors, for instance. So maximum coverage and maximum directivity at the same time. Another scenarios that you could enable is, for instance, these full duplex scenarios here. So you have a base station that is a full duplex, you have a RIS, and you want to serve a downlink users and an uplink users simultaneously, right? And those two users are not necessarily located, they're not necessarily on the same location. They could be separated from each other. So you have a users here who transmit a wave on the uplink that would be reflected by the RIS towards the directions of the base stations. And then you can have a base station transmitting a wave on the same time frequency resource. In the downlink, the wave would be reflected by the RIS, but if you have a conventional RIS, the wave would go back to exactly where the original wave was transmitted. So if you have a conventional RIS that is reciprocal, the wave from the base station would go back towards the uplink users. But here, if you have a non-reciprocal surface enabled by BD RIS, you could actually have the downlink waves actually going into different directions from the directions of the uplink users. So this is actually quite interesting because now you can serve a downlink users and an uplink users at two different locations because of the non-reciprocity enabled by those risks. You can enable wireless circulators also. So what is a wireless circulators? It's inspired by what you have in microwave circuits where you use circulators. So circulators is typically a device that has 3 ports, A, B, C, and the wave within this device only goes unidirectionally. So it goes from port A to port B, from B to C, and C back to A, for instance. And so you can enable this over a wireless network, for instance, where actually because of the presence of a non-reciprocal BD RIS, you can have a device 1 will communicate with device 2. But when device 1 goes communicate with device 2, actually, the waves do not leak towards other directions or to other devices. Then device 2 communicate with device 3, 3 to 4, and so on. So you have this flavor of the microwave circulators, but over a whole wireless network that would be enabled because of the non-reciprocity that of the beyond diagonal risk. You can have polarization conversion. So, for instance, here you have a BD RIS that is made of multiple elements, and you have two polarization, vertical and horizontal. And the vertical and horizontal polarization are actually interconnected with each other. So what that means, I can have a wave impinging, vertical polarized wave impinging on this RIS, and this RIS will then reconfigure the polarization, convert from vertical to horizontal, and therefore let the wave propagate from a vertically polarized wave into a horizontally polarized wave. So for instance, if you have a line of sight scenario here where you have transmitter is vertically polarized and the receiver is horizontally polarized, if you have a conventional RIS, the vertically polarized will be captured by the RIS, but then will not be captured by actually, you would not have this conversion or reconfigurability property of the polarization. So that means actually the wave that will be reflected by the RIS would only be vertically polarized and would not reach the receiver. On the other hand, with BD-RIS, because you have these conversions of polarizations, the wave vertically polarized will be converted into horizontally polarized and then will reach the receiver that is horizontally polarized. So that can enhance your coverage, because we know that actually polarized antennas actually is heavily used in practice. You could use this in other systems. Here you have actually a scenario where you have a transmitter with multiple RF chains, multiple antennas. We don't do any form of digital precoding, but actually we do the precoding in the electromagnetic domains via the presence of multiple actually RIS here, stacked, right? This is sometimes called stacked intelligent metasurfaces. And conventionally, those intelligent surfaces actually again diagonal RIS. So you have θ1 is a diagonal matrix, θ2 is a diagonal matrix, θl is a diagonal matrix. And all together, all those L layers of RIS, what they create a channel matrix or matrix or scattering matrix that effectively is non-diagonal. So what you can do with BD-RIS is actually effectively remove those L layers of SIM or these L layers of RIS and replace by only one layer that is actually a BD-RIS. And we can show that actually this is the optimal things to do. That will give you the maximum performance, and will come with actually lower complexity, circuit complexity, because one BD-RIS would have fewer tunable components than having L layers of actually conventional RIS. And because you have more degrees of freedom to manipulate wave, your performance gain can be also quite significant, but that depends really on the scenario. So here I give you an example here on the left side of an optimized multi-user MIMO system that is added by a RIS. So you have a RIS that is embedded in the environment. And what you do is that you optimize the scattering matrix jointly with actually the transmitter operation when you have 4 transmit antennas and 4 users to serve. And you have here conventional RIS, diagonal RIS. And as you increase the number of interconnections, you see the gain that you achieve with actually beyond diagonal RIS. So this is sum rate performance versus the number of elements that you have in the RIS. And you see you can almost double your spectral efficiencies here because you have more degrees of freedom. Therefore, you can manage the interference better in your network, and that boosts your sum rate performance. If you go to more advanced RIS like this, where you have 2 sectors or 6 sectors, again, I mentioned earlier that you can have a better 360 degrees coverage. And at the same time, you can have directive transmissions. And that leads also to actually enhance coverage or enhance sum rate performance versus the number of tunable, number of RIS elements when you increase the number of interconnections within your RIS, or when you increase the number of sectors that you have in your RIS. So in red is when you have 2 sectors, in blue is when you have 6 sectors. So in this case and this case. And the bottom one is what's often called a star RIS, which is a very specific type of BD-RIS, where you have one element on the left side here of this RIS is connected to one element on the right side of the RIS. That's all what it is. But if you enable more interconnections, you see that actually you more than double, almost triple your spectral efficiencies, because you have many more degrees of freedom to manipulate the waves and boost your sum rates. So we noticed that in general, really BD-RIS is very helpful when you have multi-user communications or when you want to transmit multiple streams. This is where you have significant gain in terms of spectral efficiencies. Maybe lots of different developments in BD-RIS. I will not talk about all of them, obviously, but this is a very recent one that was just submitted that is actually quite interesting, is what's happening when you have a multi-operator deployment of RIS. And we know that this has been a very major problem, because if you have, let's say, a serving operator here that is illustrated by the base station 1 that wants to communicate with its own users via RIS, and that base station 1 controls that RIS, right? But I can have in the network, I can have another operator that operates at a slightly different frequencies, adjacent frequencies, and whenever operator 1 will actually change the RIS, it will change the channels of the adjacent or the other operators. And this creates actually a lot of issues for those non-serving operators, because the channels actually fluctuates in a non-controllable way. And the question here is, can BDRIS actually resolve that problems? And actually, we show that indeed, with BDRIS, you have enough degrees of freedom to make sure that the channels of the non-serving operators remain constant. So you don't change the channels of other users, but you can still have the flexibility of engineering the channels of your own user that is served by this base station once. Mathematically, this translates into having very different scaling laws of the received power when you have, in a multi-operator scenarios, when you have BDRIS versus DRIS. So this is the average received signal power versus the number of RIS elements when you are in a multi-operator settings. And you can show that in the scaling of the received power when you have conventional RIS, here at the bottom is a single connected, this is a diagonal RIS, it actually has a linear scaling. So that means that your average received signal power is only linearly with the number of RIS elements. And this has been a big disadvantage of conventional RIS. If you have a single operator settings, you have a quadratic scaling. But once you operate into a multi-operator setting, then this quadratic scaling becomes linear scaling. So actually you receive power scales very slowly with the number of RIS elements. On the other hand, once you switch on to actually a BDRIS, you can actually still maintain the channels of non-serving users constant and engineer your own wireless channels. And that enables you to actually retain the quadratic scaling. And so here you have different curves that come with the number of interconnections that you have within your BDRIS. So this is the full-blown BDRIS where you have interconnection among all elements, and you can see that you have a really dramatic increase in gain, simply because you can have many more degrees of freedom to maintain the channels of non-serving users constant, and while still engineering your own wireless channels. So this is, I think, quite interesting scenario where BDRIS can really resolve the multi-operator problems. Right. So, of course, behind all those results and all those risk development, there is lots of physical modeling and mathematical challenges. And so one of the main problems that we have in BDRIS is how we going to model those risks. And to do that, we go back into multi-port circuit theory or multi-port network theory that models communication systems with multiple transmitters, multiple transmit antennas, multiple receive antennas, multiple elements of the RIS. We model this as actually a gigantic multi-port networks. And what we try to do is to analyze the relationship between impinging wave and reflecting wave across all those elements in this big multi-port network. You have NT antennas and R receive antennas and an I element in the RIS. You actually create a very large network, N-port networks. And what you're looking at is the relationship between impinging wave and reflecting wave in these N-port networks. And you can analyze this using admittance parameter, impedance parameter, admittance parameter, or scattering parameters. And then those three forms of parameters, they will give you relationship between the voltage and the current at those different ports, or actually the incident and reflected wave at those different ports. And importantly, obviously, when you have a RIS embedded into your environment, you need to have reconfigurability. So you have to be able to reconfigure your admittance matrix or impedance matrix or your scattering matrix in order to engineer your wireless channels. So what that tells you is that now you can actually operate on different types of parameters. You can actually tune the scattering matrix of your RIS, or equivalently, you can actually tune the admittance matrix, Y, or the impedance matrix of the reconfigurable microwave networks. It's all equivalent mathematically, but actually in terms of optimization, it leads to very, very different optimization problems. And it turns out that actually operating on admittance matrices is often much more efficient than operating on scattering matrices. And I will give you an explanation in a minute. So once you have a physics consistent modeling of those risks using multiple network theory, and therefore capturing the effects of the risk within your channels together with mutual coupling and a number of other actually non-idealities that you could have, then you can start asking yourself, how am I going to interconnect all those elements with each other, right? If I interconnect them more, I'm going to have higher complexity, circuit complexity, but I may have more actually performance gain. So the question is, how do we have to really interconnect them? And so the interesting observation is that the BD risk can be represented as a graph. And a graph where you have the vertices of the graph, actually the risk element, and the edges of the graph are the interconnections between the risk elements. So you hear 5 different risk topologies. The first one, the top one, is conventional risk. So conventional diagonal risk, or also called single connected risk. So I have 4 elements in the risk, and they're all disconnected with each other. Each element is just connected to its own tunable load. So in terms of graph, this means actually I have an empty graph. I don't have any edges in this graph. On the other hand, if I jump into the bottom one, here I have a risk, a BD risk, where I have between any 2 ports or any 2 elements, I have a tunable, reconfigurable admittance or impedance, right? So that leads to actually a corresponding graph that is a complete graph that I can have potentially many cycles in this graph. And so what we would like to know is, how can I achieve the same performance as the bottom one, but with the lower circuit complexity? That means the lowest number of tunable components that I have in the risk. And it turns out that there are 2 major observations that we obtain. Is the first observation is that you don't need all interconnections. For instance, this risk here that is called a 3-connected risk, that is a risk that is connected but does not have any cycle. So the graph is connected but does not have any cycle. This risk, for instance, is optimal. We'll achieve exactly the same performance as this one whenever you have a single stream transmission. So if you have single stream transmission, you want to maximize your SNR, for instance, you don't need to have this complicated risk. You can just rely on this one. And that really actually leads to a much lower number of tunable components than if you have a full-blown or fully connected BD risk. So that's the first observation. The second observation is that now if you want to increase the number of streams that you want to transmit in your network, you actually need more interconnections in order to achieve the optimal performance. So for instance, if you have a point-to-point MIMO systems and you have a risk inside your channel, if you want to transmit 1 stream or 2 streams or 3 streams of information, as you increase the number of streams, you need to increase the number of interconnections. So those actually, and we know the optimal graphs that achieve those optimal performance, and therefore we can potentially design those risks inspired by those graph optimal architectures. Right, so those are actually examples of different risk architectures. The conventional one, a fully connected, where you have 4 elements, but you now connect all elements with each other with 1 tunable component between any 2 elements. You can divide them into groups. So that if you need group, you have interconnections, but then between groups, you don't have connections. This is a tree-connected or 2 different types of tree-connected. These are actually optimal for single-user MISO systems when you transmit 1 stream of information. And then if you want to go to more multi-user MIMO or MIMO transmission with multiple stream transmission, then actually other architectures have been developed, band-connected, stem-connected, that we know are actually optimal for those scenarios. Really optimal when we have an ideal setup. Ideal means you don't have losses, so you have lossless systems, essentially. Right. So I will not go into, I could spend hours talking about BD risk. There are, the bottom line is really to understand how can you engineer or have maximum flexibility to manipulate microwaves by actually enabling interconnections between those risk elements that enable you to really reconfigure the coupling that you have between all those elements and engineer the coupling in a much more, in an artificial way, if you like, in order to create scattering matrix or actually impedance matrix or admittance matrix, it's actually not simply diagonal, but where you could make use of all possible entries of those matrix. And you can show that not only this generalize all conventional RISC architectures, you can have phase and magnitude control, you have significantly higher performance in terms of spectral efficiency, especially if you go to multi-user communication. You can have hybrid modes with different architectures like this, increasing coverage. You don't need all interconnections. You can show that you need fewer resolution bits. So each element, you have more interconnection, but each element relies on actually fewer resolutions. So 1 bit resolution is actually sufficient. It works much better when you have a compact deployment. So when the RISC elements are very close to each other, you can actually engineer the coupling, the mutual coupling in a very smart way. You can enable polarization converter. You can enable, SIM with just 1 layer of SIM. You can use this for sensing. You can use non-diffusive possibilities to actually enable full duplex wireless circulators. You have significant gain when you have a multi-operator deployment and so on. There are also cases where you don't have gains, right? So the worst case for RISC is really when you have a single user, line of sight, no mutual coupling, no same polarization across all elements. In that case, you can show that the gain of BD RISC is actually in far field. The gain of BD RISC then is decreasing towards the gain of D RISC. But also challenges. Careful about losses, obviously, because you have interconnections. So actually, if you have losses on those interconnections, the performance gain may decrease. And also, the tunnel estimation overhead is actually not the same. So this has been lots of research, or ongoing research in this area across those different areas to try to improve the performance as much as possible. So lots of opportunities and new problems to solve. For people actually involved in optimization, and also very interesting problems, because you can optimize, you operate on theta matrices that actually so on unitary matrices, so you operate on manifolds. Or you can operate and optimize on your Y parameter, your admittance parameter, and this gives you actually a better optimization problem in the sense that actually you capture the sparsity of those RISC architectures better in the admittance domain compared to the scattering domain. So even though they're physically equivalent, admittance, impedance, and scattering, actually in terms of optimization, it leads to very different problems and different complexity. Right. So then the next stage is saying, well, how can we make use of some of those ideas of BD-RISC to do now computations? And the core idea of BD-RISC is really that you enable tunable interconnections between RISC elements. So can we use those interconnections to now do really computations? And so this leads to actually this emerging area of microwave analog computer, where you have essentially on the left side, you have a microwave network here, where a microwave network is actually a network of interconnected, for instance, radio frequency components, or it could be an abstract representations of a metamaterial. But bottom line is that you have inputs and you have outputs, and within this black box, you have some potential interconnections, right? So you apply input signals, the signals actually propagate through this network at the speed of light, or close to the speed of light, and then you read out the output of this network, the output. And so you actually compute, in a way, a certain function f, a function of the input u, a function of potentially the parameters of these networks, and you compute a function f instantly. So at the speed of light, these functions would be computed. And the question is, well, what kind of function can we compute? And so you can do some operations. If you have a non-reconfigurable network, for instance, so you don't have any tunability on this network, then what's going to happen is you can do you have a linear systems, because typically microwave device or microwave components actually are, or at least the passive one, they actually are linear. So you actually can do some form of matrix vector multiplications here. So W will be actually characterized by the microwave networks, and U would be your input. So you would perform matrix vector multiplications directly in the analog domains at the speed of light or close to the speed of light with a very low complexity, because you don't need any form of digitizations in order to do this matrix vector product, right? So in this case, your computational complexity does not grow with the size of the input and the size of the output, in contrast to actually digital systems, where if you do this matrix product multiplication, it will be actually a complexity will scale with the number of inputs and the number of outputs, so the size of actually those matrices. So to give you I will give you an example in a moment. If you have now reconfigurable networks, that means actually you have some element within this network that you can tune. You have additional parameters to play with. You have your input U, and you still have a linear system. So you have a linear, your input U is here, but your W matrix that is actually dictated by your microwave networks could now be a function of a few tunable parameters, P1 to Pk. This could be tunable component within your networks. And what we can show is that now your W could be actually a nonlinear function of those tunable components. And that's quite interesting, because now you can do more complicated computations. Let me give you some insights. This is actually a relatively simple circuit here. I have two inputs, I have two outputs, and I have within my microwave network here, I have four tunable or four actually admittances or impedance here that actually connected with each other among those four ports. If you apply Ohm's law, you can actually see that actually this is actually performing as a form of voltage divider. So you have your relationship between your V and U is given by this relationship. So this is your matrix W I was talking about before. And you see that in this case, you have still a system that is linear in U, but is nonlinear in those tunable, in those parameters G's, right? So it's, for instance, function in G11, the inverse of G11. So this is an example where actually is very simple circuit that tells you that you could do some form of computations. You can compute functions that are nonlinear in those tunable parameters, function G. So can we actually formalize this in a more general way? And the answer is yes. So imagine now you have a network here. I have multiple inputs. I have multiple outputs. And I have a microwave network where I have interconnections between all those elements. And my question is, what is the relationship between this input here, U, and the output that I can measure at all those ports? And in particular, the output here, V3 and V4. Can we formalize this? And so we can do that. You can write the actually circuit equations at the input, at the output, and within this microwave circuit. And what you can show is that your output voltage V is actually a function, linear function of your input voltage U, as we had before. But now your matrix W that we had before, that was abstracted, actually now is given by this weird expression here, that is a function of 4 blocks, A, B, C, D. And those A, B, C, Ds actually block of a matrix Y, and this matrix Y is actually the admittance matrix of this microwave network. So the admittance matrix, it gives you the relationship between the current and the voltage at those ports of these microwave networks. And the entries of this admittance matrix actually itself function of those tunable parameters, those tunable admittance that you have within the network. So what that means is that by changing those tunable admittances, you change the whole admittance matrix of the network. By changing the whole admittance matrix of the network, you change the values of ABCD. And by changing the values of ABCD, you change actually the function that you can compute here, right? Now, what is very important is that this function here, that is a function of, performs matrix product, matrix inversions. This computation of this function is done directly in the analog domain at the speed of light or close to the speed of light without having any form or any digitizations. I don't digitize any signals here. The physics of the network can compute this function for me directly. Okay, so no matrix inversions, no products as we classically do in digital computing or digital signal processing. It's all done directly by the physics of the microwave networks. So where is this interesting? Well, we can compute this with microwave networks. Now let's go back and see what we do in signal processing. So we have a linear observation process, and you have something like this: y is equal to h express n. Very often, you want to estimate x given some estimate on h, and given the knowledge of the second-order statistics of x and n, typically. So based on the observation y, right? And one typical well-known estimators is this linear minimum mean square estimations, and you see very unique similarities between this expression and the above expression. In other words, d minus 1, the inverse of d, would be the current matrix of the input. C would be actually the Hermitian of the channel matrix, or the observation matrix, H, and so on. What that means is that we could now use the microwave network, or this MILAC, to compute LMMAC directly in the analog domain without having to do any form of digitizations, or any actually variance of this expression. For instance, when you do least square, you could do this directly in the analog domains. And what we can show is that the computation complexity of doing this is actually significantly lower than when you actually do this in digital. So in digital, performing this form of computation would actually scale cubically with the size of the matrices, because typically matrix inversion is done with complexity n cube. Doing those operations in digital, in analog, instead, give you a complexity n square. And why there is still some form of complexity is because you have to be able to adjust the tunable components. So you have to be able to, once you want to compute this quantity here, go back and say, well, I need to set the value b to actually a specific value, and therefore I need to tune each of those admittance in a certain way. And this takes some form of complexity that is reflected in a form of computation complexity. But that scales only in n squared, and we have closed some solution for this, but that has some complexity. So that means that now, in analog, you could do matrix inversion in n squared, which is absolutely not feasible with any digital computer unless you have very specific matrix with a very specific structure. But here we hold for any form of any matrix. Now you can use this, since LMMAC or least square is very useful in communication system, especially when you do MIMO processing. You can use this to create a new MIMO architecture, so a microwave linear analog computer architecture for MIMO processing. And so, for instance, I could use this microwave network at the transmitter to perform now some form of pre-coding directly in the analog domains. So zero forcing beamforming or regularized zero forcing beamforming is a particular case of LLMMAC, and I can do this directly now in the analog domains. I don't need to have a digital pre-coding to do that. Or I can do this at the receiver, where actually I do the combiner directly in the analog domains, right? So if you do that, well, you can have a radical change in your MIMO architectures and a radical impact on your computational complexity. So this is a new MIMO architecture where I don't perform any digital pre-coding. I have a multiple MIMO systems on the downlink. I have multiple transmit antennas, multiple users to serve. And now I will do my pre-coding, my zero forcing pre-coding, for instance, is a particular instance of the LMMAC, so I can do this directly within my microwave network. So I don't perform this pre-coding in digital, I do this directly in the analog domain. So matrix inversion is done by the physics of the microwave networks directly in the analog domains. And if you look at the sum rate performance of a multi-user MIMO system as you scale the number of antennas and the number of users to serve versus the computational complexity of performing this operation, you have this graph here. So in blue is when you perform this operation in digital. So you're going to have a certain sum rate, spectral efficiencies versus computational complexity. And as you scale the number of antennas, you go from 5G, that is somewhere here, 100 antennas, maybe a few tens of streams. To 6G, maybe you have hundreds of antennas, maybe larger number of streams, all the way to 4,000 antennas, 4,000 streams. You have massive increase in spectral efficiency. You have also massive increase in computational complexity. With this MILAC architecture here, you can actually achieve theoretically the same spectral efficiency, but you can do this with massive reduction in computational complexity. So you see here the gap. You have for fixed computational complexity, you would have a massive spectral efficiency gains, or for fixed spectral efficiency, you have a massive reduction in computational complexity. And this is because you don't perform the matrix inversion in digital. All this is done in analog. You don't perform this matrix vector multiplication at symbol level, at symbol rate. It's actually done directly in analog at the speed of light. So that reduces massively your number of your computational complexity. So now we have three architectures. For MIMO, we have the digital one, conventional. We have the conventional hybrid digital analog, where actually the analog part is just some form of phase shifters. That is being used more for millimeter wave MIMO. And then you have these MILAC architectures where now you actually get rid of completely digital precoding and you perform everything, all your operation directly in analog domains. And what we can show is that theoretically, you have the MILAC has the same performance as digital because you can perform directly the LMMSC in the analog domain. It comes with actually a significantly lower number of RF chains because the number of streams is equal to the number of RF chains, in contrast to digital where the number of RF chains is equal to the number of antennas. So that actually gives you the lowest number of actually RF chains. It also decreases the resolution of the ADCs and the DACs because what you feed in each RF chain is now one modulated stream. It's not a linear precoded versions of modulated streams. So that actually means that we can rely on lower resolution ADCs and DACs. And you don't need to do operation at symbol basis. You don't need to multiply your precoder with your symbols, at symbol rates, because this would be done naturally by the physics of analog propagations. Right. So with this, I will conclude here. And sorry for being a little bit longer than expected. So we looked at raising the question of whether actually digital only would be sustainable and scalable for future systems. Looking at the fact that analog computing has received a renewed interest to try to not replace digital computing, but actually try to complement digital computing to capitalize on the strengths of digital and analog to do actually faster computation, more energy and computational efficient computations. We tried to look at different domains that exist. I've talked very briefly about optical in-memory and metamaterials. What I showed you is actually you can do with microwave networks, which actually relies on really off-the-shelf component. You can create actually a computer directly in the analog domains, and you can do very meaningful computation with this. We talked about beyond diagonal RIS and the MILAC. Both of them relies on reconfigurable microwave networks because they both have interconnections between elements. So the tunable interconnections is really crucial to enable those two technologies. There are lots of interesting problems on the BD-RIS design, on the whole optimization, on the channel estimation problems, the signal processing, how you can use machine learning to discover new architectures. This is very interesting, especially when you captures all the non-idealities of the physics, of the propagations, of the losses that you can have, the quantization that you can have on the tunable components. You can really discover, in the same way as you discover molecules using graph neural networks, you can use graph neural networks to discover BD-RIS architectures, how you model BD-RIS, how you come up with physics-consistent modeling, what are the use cases where actually you see really large gains of BD-RIS, and how prototyping experimenting this, because this is obviously more challenging in terms of hardware design. So interesting research frontier for communication engineers, and we have these special interest groups in IEEE on these topics. And then I talked briefly about analog computing, especially this MILAC, and I showed you that you can do matrix inversion in complexity n squared. This leads to actually new MIMO architectures where actually all your precoding and combiner could be done directly in the analog domain. And that leads to actually significantly lower computational complexity, several orders of magnitude lower computation complexity. there are also lots of interesting problems, how you model those MILAC, how you design this, how you optimize them. Very similar to the BD-RIS, but it's quite different because you do computation directly. And how can you prototype this also? One important aspect that I want to really emphasize that I didn't say so far is all the computation you can do with analog computing and with MILAC, it will never be as precise as what you can do with digital. So you need to come up with use cases where actually it makes sense to do computation and you can afford to have less precise computations. And for instance, in MIMO is very relevant because when you do MIMO precoding and you do those matrix inversions, you always rely on an estimate of the channels, and the estimate of the channel is never known perfectly. So it doesn't make sense to have super accurate computations when actually your input age is already inaccurately known. So this could be one interesting, that's why I think MIMO would be an interesting use case for analog computing. And obviously you have to be careful about all the hardware limitations and capitalize and really model this as part of your systems. So far, this is something that has not been really done, given the very early stage of the technology. So if you're interested, we had also an special interest group in IEEE on these topics, and we have, similar to BD-RIS, we have a website for this where we have also organizing a webinar series. And we just started this one on analog computing not long ago, the past few months. So with this, feel free to look at those web pages if you want to have some references. I give you here some reference. This is not comprehensive. There are other groups working on this, increasingly working on these topics. I think a good starting point is this tutorial that we wrote not long ago that gives you really the fundamental to model the BD-RIS, to optimize BD-RIS, and looking at application of BD-RIS. On MILAC sites is much more early stage, so the few papers that exist actually all on arXiv in the past few days or few weeks. Just earlier this week, I think there were 2 more papers on arXiv, so it's still very, very early stage. And with this, I want to thank a number of actually past or current PhD students and postdocs who are or have been actively working on these topics, and I would be very happy to answer any questions that you may have. Also, feel free to reach out if you have any questions. Thank you very much.